Well, hi everyone. I'm Gema Parren. I'm part of the Innovation Labs at BBUA. Today, I'm here as an open source developer to give a dive into the Starcraft 2 library released by DeepMind and Blizzard this summer. This talk is going to be separated into two parts. Okay, in the first part, I'm going to dig into artificial intelligence reinforced learning concepts, and the second part is going to be centered on the library and my technical contribution to it. Here you have all my contact, so please feel free to reach me. So when we are digging into data and we are doing machine learning, we are thinking about how we have data. In supervised learning, we do have tagged data in which we classify or predict things. We can use different algorithms like linear regression, naive Bayes, random forest, or even support vector machines. In this case, we know how the data works, how are the labels. So we learn actually by it. In supervised learning, it works the opposite way. We do have not taken data, and we find patterns on it. We discover things. We can find algorithms like K-means or even neural networks. But here today, we are not going to talk about supervised learning or unsupervised learning. We're going to talk about reinforced learning. What is reinforced learning? Reinforced learning is learning towards a goal. We don't have data that is taken or that works in a certain way. We do have a goal, and we train an agent to learn that goal. For that, we do some kind of decision Markov process and some mathematical environments that define it. So at the end, machine learning is classified by the method or the way that we learn from it. In the case of reinforced learning, it is based by how the way it learns while interacting with the environment. So every time, everyone can ask you about what is the method that you are using with machine learning. You can always ask also, how is that learning? And we will classify, taking into account. OK, so now I'm going to dig into reinforced learning, starting to talk about the perception-action learning loop. So when we do have reinforced learning, we do have an environment, a set of conditions that defines how it works. But we do have an agent, a program that is going to be trained to tell us how it works. So there is an interaction in between them, taking in states that the environment is sending to the agent. So it's interacting with a policy, and then it turns back an action. So and then the environment makes a decision. So at the end, it's like a loop in time in which the environment is interacting with the agent, giving a reward. The environment is no more than the context of that learning. It must be defined with the actions and the time. But we're in reinforced learning are seeing a lot of video games as environment. Why those video games? Because video games are environment that talks about general purpose learning. Behind those video games, there are systems that are capable of learning how to adapt to the real world. So today, it might be video games, but tomorrow it will be guts in your stomach trying to survive or not survive, or robots trying to catch something. So at the end, these environments, video games, are an abstract method to those general purpose learning. The agent is the program, is the learner, is the decision maker. The goal of the agent is to learn the policy that maximizes the reward. The agent uses this knowledge of state transitions in time. So at the end, it's a program that is learning by itself to improve the policy. So OK, what is a policy? The policy is something that really defines the behavior of the program at a given time. At the end, in reinforced learning, we are improving one step at a time that policy. So at the end, we have like the best way to reach that goal. So take care that at the end, this reinforced learning wants to reach a goal. So we have states, and we compute probabilities about these actions. We use a neural network to give us the probability of which action should be better. So at the end, the agent is taking an action that is moving towards that goal. And when they reach the goal, they give out like the reward. So at the end, I have like an actions. I take one decision, and then it gives me the return. 2 years ago, DeepMind released a neural net for Atari video games. There were like more than 2,600 video games that at the end, they're like different reinforced learning environments in which the goal was changing from one environment to another. So they have like different set of general purpose learning goals that they could like implement on each Atari game. So I encourage you to the healthy aesthetics not to see video games anymore, but to see abstract problems that can be solved with different approaches. So at the end, okay, I have an input and I have an output. I have to give something to that policy. So we have like some spatial features. I mean, where it's going to move, it's going to go left or to go right, or not spatial features. You mean if I'm going to make a point, if I hit the goal. So that is like how we feed the policy to really, really work. So at the end, the output is the decision that I want actually to make. So at the end, it's important to know that I have like a set of inputs that is going to be like released with the environment, and a set of outputs that is going to be how that interaction really works with that environment. So here, if everything is working good, there should be a video, but it's not. Okay, so at the end, what is all this all about? It's about producing policies or producing different kind of neural networks that can be related to these environments. People have been like surprised as this game in a few weeks of training can actually like have a superhuman performance. So and it like has improved like the ethics warrior community. So it might be the time to think about human and machines collaborating in a complementary way, in which machines can do a certain kind of things in a more efficient way than humans, but humans still can give like a lot of abstract thinking into machine learning. So maybe it's the time to accept that complexity of systems that are like maybe in some cases are too much for humans, and that's a challenge for us as a society. Reinforced learning is not perfect. All machine learning approaches have its challenges and a way to go towards them. I'm going to talk about the three that I consider like more relevant. First, trial and error. A system must be learning and must be trying new things and trying all the actions for really to learn. So the optimal policy must be inferred by that trial and error interaction with the environment, and the only learning signal the agent receives is the reward. So at the end, you need time, and you need that state times to really give like a significant step with reinforced learning. Besides that, we have like this problem, the credit and cycling problem. Agents at the end must deal with long-range time dependencies. So the consequence of an action comes and materialize a lot of time after the decision is actually made. So to learn, it has to learn that there are different rewards in different times with different consequences. So time here is very important to the agent to know that in the long term, they might have take the good or the bad decision. Besides, we have the exploration versus exploitation dilemma, in which it says that when should the agent be perceived be taking an action that is not optimal in order to explore their environment and potentially improve that model, and when it's just exploit it or be greedy and go into that optimal action. So at the end, it's more or less how that human thinking empirical approach works. If I take that decision here and keep with this, it's going to be good in the long term or bad term, or should I now exploit or take that opportunity or this decision to make it better? So far, we've been those Markov decision processes that at the end gave that environment and agent interaction and define a policy. If I have to tell you only one sentence about reinforced learning, I should tell you that the goal to reinforced learning is to learn from the environment, okay? And to maximize a policy that is called the behavior. When you dig very much into it, you can say, okay, I can take a value function, a quality function. I can go into Bellman's. So it's the concept is quite clear, but when you get dig into it, the policies are huge and depend a lot on your problem. So Starcraft 2 has been released as a reinforced learning environment. What does it mean? It means that we have Starcraft 2, that is that real strategy game, as that environment in which agents are going to interact for taking decisions. So why Starcraft 2 and why now? Because now hardware and software and the current state of industry allows Starcraft 2 to be a complex enough environment, but also presents some challenges for agents. So at the end, the value proposition of this is to propose different policies and different neural networks that can be used as an agent to learn and afterwards be implemented into other problems. So a Starcraft 2 learning environment loop, as we have seen before, works with the API, in which you can actually call the API, interact with the API. It gives some observations in terms of non-spatial features and spatial features. Remember that we talked before about those actions. And then we get into the agent. There is going to be a neural network. And that neural network is going to process all the actions given in the game, and it's going to return the most beneficial action that should be taken in that time. Okay, so AtariNet has been released 2 years ago and has been iterating around that. And the first approach that DeepMind had was to try AtariNet on this environment. I'm going to now explain which are the implementation of that neural network on StarCraft 2. So we do have a convolutional neural network that is going to both process spatial and non-spatial features. And we do have other ReLU layer that is going to, at the end, two processes to have a state representation. That is the input that we are going to put into our program, okay? So we have a CompNet that at the end it processes images, and one node feature layer that it has data. We process that into a state representation, and the output we have a value, it's going to be a score, but also a spatial and not a spatial policy, in which it's going to tell to the units how to move and where, and what should they do? Because in StarCraft 2, you can actually move your units, you can do nothing, you can build things. So it's no longer about Atari games, the move left, move right, throw a ball. So the complexity here is bigger. That's why neural networks are implemented here. The policy search, it's something that they have current under development and have open source. The first neural net or agent net architecture that they released in the paper was the convolutional net that we talked before, that was like taking the spatial features and the non-spatial features. But here they were like combining all into one state representation, not one hot encoding, huge hot encoding. And then it was like giving apart and a spatial agent policy in terms of ComNets. What does it mean? This means that actually the neural net, the new neural net for StarCraft 2 can actually see what is the result, okay? So it can like process how it's going to work in a spatial policy. And at the end, it's going to be it's going to give also like an action. So here is like again kind of a changing of the paradigm, because it's no longer moved to the X, going to one place to another, but the convolutional neural net gives you an image of where should be. Inside the Starcraft 2 liberation library, there are like several, you can play long-term games, and you can play the mini-games. The mini-games are short, goal-oriented mini-games in between protos for giving you like hands-off approach. At the end, you can like take what are the common problems of machine learning and build abstract models that are like related with mini-games. And you can like test your agents. So also like mini games are great for a start. So if you can download the library from GitHub, and you can start on your own machine to see how those mini games work on trained agents and non-trained agents. This was actually what I was doing. I don't know if. Okay, so here should be like a video in which you can say like how the minigame is with a non-trained agent and it's actually functioning with a trained agent. I think it's starting to run, okay. So here, like, what is happening is that Starcraft 2 is actually running in your local machine. You don't really need to have the Starcraft installed on your machine or a Battle.net account, because it's open for developers. And this mini game is called Marines versus Roaches. So you can see in your left side how the Marines are actually like exploring the map, going one place to another, and actually not like winning all the battles. In the agent train, they are like going straight forward for killing roaches. And you can see that at the end, the number of Marines as a reward is the Marine to be increased. You can see that actually the number of Marine increases with time. But here in the same map, you can try different kind of neural net architectures that are going to work better or worse, depending on the case and depending on the problem that you want to solve. In this case, the defeated roaches map, they tested like the Atari net we saw before, a fully convolutional net, and a fully convolutional with an LSTM with memory, okay, for seeing like how was the performance. So here, if you see like at the end, at the beginning with the batches, the fully com and the Atari net is giving like best performance. So that means that the agent at the beginning is learning faster. But as the time goes by, the final performance of Atari net and fully convolutional net goes down. So goes down rather than the convolutional with memory. So this means that learning before doesn't mean learning better, okay? It's important to test those agents in the long term to see how final performance is going to be. So after opening some issues, making a Minigames contribution, and starting like scripting my own bot, I have like an interaction with the project owner of DeepMind, and told me to apply for BlizzCon workshop. I was there a few weeks ago with a huge community of people that is actually working with this library to go one step further with this. And now I'm going to tell you about what has been my personal contribution to this. So are there any players of StarCraft 2 here? Well, some tiny ones. Okay, so I've been playing StarCraft 2 since 5 years now, and I find it like a huge strategic learning game. And my favorite race is Protoss. Protoss is an alien race that it's like hard to play because the thing is that the production of the army Protoss is high cost. So how you balance your micro strategy, how you balance all your units, it's very important because units are very expensive. So the centric unit is a unit that you need like some development to actually build it, but it's very important. Why is a centric unit significant and can be a contribution for the artificial intelligence community? So the centric unit can do three things. It can have like a guardian seal. It can protect your army. Okay. Can have like a force field. It can have like set a distance in between your army and your opponent's army, and can do hallucination. They can pretend, they can make fake units that actually don't exist to both fool your enemy into production and absorb damage. So why is that significant? This is significant because this affects directly to the micro strategy, but this action affects to your long-term strategy. Okay, so how you play a centric unit can have like a significant performance in your strategy and opponent's strategy. So I was working with this unit to see, okay, so if I work with this unit, I can also put in design how long-term can work with a neural net or with an agent inside StarCraft 2. So the first time I proposed what is called like an Arrowhead formation, that it's famous in Rome and ancient armies, in which I put like the significant units in the central place, actually a defense for the Protoss, and an opponent's army that have like the attackers most significant here in the center as well. At first, I was like making this, having into consideration the damage per second that both armies were actually doing. But then, talking with the community and with other developers, they came like the idea, okay, so why don't you imbalance those armies? So you force the Senti unit to make force field or hallucination, so the agent can learn before, or you can test how that learning is working in time. Besides that, I started to see more community forums in which the balance was like a better design. And in my third iteration, I was like directly working on how one of the hallucination functions should work. So at the end, I was like forcing to it to say, okay, you're going to make hallucination and learn as soon as possible. So now I'm going to show you the results, okay? So here we have like the random agent. The random agent starts playing and starts like hallucinating randomly and start exploring the map. And at the end, okay, it defeats the enemy, but it's not an optimal strategy, and as it is like actually like given in one hand and in other hand, and not very clear. But then I started to play with the scripted agent. The scripted agent started actually to make hallucination much more straightforward, okay? And actually, like, it was winning, and each time it win, I give it like a final reward to set one more century, okay? So at the end, the result was, it was like using hallucination. It was an imbalanced melee, but when he was like using hallucination, it was actually winning. So here you can see that it starts like with 4 centuries, and at the end, it's dominating the world. So, okay, so why are you doing this? Why are you focusing on StarCraft 2, and why this? I'm learning reinforced learning. Reinforced learning has huge time-dependent challenges and had a lot of concepts that can be implemented, but StarCraft 2 is kind of the playground for this, okay? So at the end, you can, the knowledge that you get for this can be implemented to your businesses, to any problem, to health problem, to robotics, to images. There are like tons of challenges that can be like put with this. So if you want to do something with reinforced learning, I'm only going to tell you 3 things. Design the environment, okay? Please give the set of conditions that is going to make your problem work, the set of observations and of actions that is going to make it. Have the goal in mind, okay, the problem that I want to solve is this. I don't have clear how I'm going to solve it, but I'm going to experiment with an environment and with an agent and with a policy to try. And then the policy. The policy hasn't to be a neural network strictly, okay? There are hundreds of approximations to that policy that actually can be like game-changing to your problem and can be like quite more easy to implement to solve it. So that's it. Thank you very much for coming. I'm actually building a community around this. So if any of you feel motivated and want to make part of it, it's not only about programming, it's also like about making environments, about designing. So I'm happy to help with you. I don't know if you have any questions. We do have time for 2 questions or so.